Good afternoon. Here the subject is kinematics and theory of machines, and the chapter is vibrations, waves and vibrations. This is a subject of third year according to the curriculum of MACOUT, that is one university. Anyway, this subject belongs to the Department of Mechanical Engineering, and here this is the first lecture in this YouTube channel. I have more than 6 or 7 channels are there. Okay. Anyway, I don't want to waste time by talking about all those channels. Here I am directly starting the topic. The first topic from this chapter, that is waves and vibrations. Paper is theory of machines or dynamics of machineries or dynamics of machines, etc. Different names are given in different universities. So here we are talking about longitudinal vibration of a spring. There is one spring hanging from the ceiling, and at the end of the spring one weight is attached, and there will be longitudinal vibration of the spring. Let me draw the same. Here, suppose this is the ceiling, okay, and here this is the spring, okay. This is the spring. This is vertically hanging from the ceiling. This spring is hanging, okay. Now if you attach one weight at this end of the spring, suppose that position is this one, what will happen if you attach one weight? So there will be some elongation of the spring due to this weight. There will be some elongation. Say the weight is W, okay. So elongation, that will be measured somewhere from here, which is the intersection point of the two diagonals of this rectangular weight, okay. So here, from here to here, this distance is due to the attachment of this weight W, okay. Suppose this deflection of the spring means elongation of the spring, that is called here deflection. So elongation of the spring is delta due to the attachment of this weight W. If M be the mass of this weight, then W is what? W is how much? Then W is equal to M into Z. G is what? That is acceleration due to gravity in SI unit. The value is 9.81 meter per second square. That is known to you. And M is the mass of this attached weight. Okay. So in that case, you will get W is equal to mg. So this deflection is due to the attachment of this weight. Now, if you, just by using your hand, if you pull this weight in the downward direction, vertically downward direction, then there will be more deflection. Okay. Suppose the next position, when you are using your hand or by any means, you can do the same. Okay. Suppose this is the final position of the weight W. Let me check whether everything is visible or not. There is no helping hand. Okay, fine. Everything is visible. Every now and then I need to go beyond the camera to see whether everything is visible or not. Okay, anyway. So now everything is visible. So there is no problem. And here, so this is what? This is the, here again, this point will be used. Suppose this deflection is, or elongation in the vertical downward direction is X. Okay, means you are using your hand or by any means, you are pulling this weight in the downward direction by an amount of X. Okay, so initially in this condition, the equilibrium equation. That should be what? Equilibrium equation in this condition. There will be tension acting in the upward direction and in the spring, and weight of this block will be acting in the downward direction. One more thing that I have missed to tell you, that is, this spring is considered to be massless. Why? It should have some mass. It is made of metal. Okay. Just to make mathematical simplicity, just for the sake of mathematical simplicity, mass of this spring is neglected. Okay, and this negligence is possible only when the mass of this spring is very, very small as compared to the mass attached at the end of the spring. Okay, in that case you can easily neglect this weight or this mass. You can easily neglect. Always there should be some comparison. Without making any comparison, nothing can be neglected. Okay, so this mass of the spring will be considered as 0. Only this mass will be considered for mathematical calculation. So here, in the downward direction, what is the force? In the downward direction, the force is W. In the upward direction, there will be some force which will be equal to W, because this is in equilibrium condition. After the attachment of this weight, this is in equilibrium condition. So let us suppose that S is the stiffness of the spring. Okay, what is stiffness? You know this thing. Okay, it is elongation per unit. Per unit what? What is S? You know, W is weight, S is what? That is stiffness. So you know the meaning of stiffness. It is equal to load per, means force per unit length. So here, if S is the stiffness of the spring, then S into delta is the upward force, where delta is the deflection due to this weight W. Okay, it is S is equal to what? It is weight per unit deflection, or load per unit deflection, or force per unit deflection. S is defined that way, stiffness. Okay, so here you can see downward force is W and upward force is S into delta. So in this case, here I can write W is equal to S into delta, where S is stiffness, and in the next line we can write W is equal to what? It is mg. So mg is equal to S into delta. In this position, okay, the second one. In the third case, this one, when you are pulling this weight W in the downward direction, then in that case, what will be the required mathematical equation? When you are holding this weight by your hand, I am not going to write that equation. Okay, you are holding the weight by using your hand. As soon as you are releasing the weight, it will start moving in the upward direction. This is known to you because this is spring. So this weight will start moving in the upward direction. I am going to write the equation just at that moment whenever you are leaving the weight. Okay. So in that case, what will be the equation? So in that case, since it is free, you are not holding the weight at that case, at that position or at that moment. So in the downward direction, same force W will be there. But in the upward direction, total deflection is delta plus X. That is the total deflection in the upward direction. So in that case, the force will not be S into delta. In that case, the force will be, in the upward direction, the force will be S into delta plus X. What is that? S into delta plus X. Okay, that will be the upward force. I am using this arrow to show you that this is upward force. And what is downward force? Downward force is W, which is equal to mg. Okay. Then what is the net downward force in that case? Net downward force. What will be the net downward force in that case? That is equal to this downward force minus the upward force. Okay, let me again check whether the right hand side is visible or not, and I can see that right hand side is also visible. Okay, so net downward force, this force downward, that is mg minus this force, s into delta plus x. So this is what mg is what? Previously we have got mg is equal to s delta at that position. So you write s delta minus this s delta minus s, this is x. So this s delta and this s delta are cancelled. So remaining thing is minus sx. So this is what? This is the net downward force in the downward direction. Stiffness is a positive quantity, x is also a positive quantity, and there is one negative sign. So this implies that actually there is no net downward force, there is actually one net upward force, and due to the presence of that force, positive sx, okay, that means in the upward direction. This is negative sx, that means actually the force is acting in the upward direction, and that magnitude of that force is s multiplied by x. And due to the presence of that force, the weight will start moving in the upward direction. Okay? Okay, fine. So, that is the resultant force. So, this is the resultant force. So, if since here x is the displacement, then if x be the displacement, then you know that d2x dt2, second order derivative of the displacement with respect to time. Here small t is time. Second order derivative of displacement with respect to time is nothing but what? Is nothing but acceleration. So this is acceleration. Okay. This is acceleration. So this acceleration multiplied by mass m into d2x dt2, this becomes equal to force. Okay. So this is equal to this minus sx. Okay, so we have assumed there is some acceleration since force is present, so acceleration must be there, and that acceleration is denoted by d2x dt2, and mass of this weight is m. So m into this acceleration is the force, and that force is due to the effect of this minus sx, due to the presence of this minus sx. Okay. Therefore, this can be written in the next line as d2x dt2 plus s by m into x is equal to 0. And you can see that there is a similarity between these two equations. This is equations for our case, and the standard equation for simple harmonic motion is d2x dt2 plus omega square x is equal to 0, where omega is the natural circular frequency. Natural circular frequency is omega. So this is the equation for simple harmonic motion. So comparing this equation and this equation, we can say that omega square is equal to s by m. Therefore, we are getting omega is equal to root over of s by m. And since this is natural frequency, therefore the letter n as a suffix is used with omega. So you should write here this way. Omega suffix n for natural. So natural circular frequency is equal to root over of s by m, where s is the stiffness of the spring and m is the mass attached at the end. Okay. So omega n is this. Therefore, what is the time period of oscillation? Say we are using capital T to denote time period of oscillation. Then time period, you know that that is equal to 2 pi by omega. This is standard equation. It is known to you. So T is equal to 2 pi by omega, and since we are using omega suffix n, so here also you should write that thing, omega suffix n, and now put the expression for omega n, which is equal to root over of s by m. Then what you will get? Here you will get, after putting the expression for omega n, you will get here 2 pi into root over of m by s. Am I right or wrong? Right. So this is the time period of oscillation. And what is the frequency? Natural frequency. Natural frequency. Frequency is denoted by f. Okay. Frequency is denoted by f. And since it is natural frequency, so suffix n is used. Okay. So natural circular frequency is this. And we know that frequency is equal to inverse of time period. That is, Fn is equal to 1 by t. So if you write the expression for t, which is this one, then what you will get? You will get here 1 by 2 pi into root over of s by m. Again, I need to check whether everything is visible or not. Yeah, everything is visible. There is no problem at all. So this is frequency, natural circular frequency in terms of stiffness and mass. This is time period of oscillation in terms of stiffness and mass, and this is natural circular velocity, not frequency, it is velocity. Okay, natural angular velocity is equal to this much. Okay, and if you want to write this stiffness and mass in terms of that deflection, then you will get what? You know that from here what we are getting? Here s by m is there, and from here what we are getting? S by m. So you will get, this is equal to g by delta. Am I right? G by delta. So this s by m can be replaced by g by delta. So in that case you can write omega n is equal to root over of g by delta. This way. Then time period, this can be written as, here m by s is there, so m by s will be delta by g. So that is equal to 2 pi into root over of delta by g. Okay, and this natural circular frequency Fn, that then can be written as what? It is 1 by 2 pi, and s by m ratio is there, and s by m is nothing but g by delta. So this is equal to this. Fn is equal to 1 by 2 pi root over of g by delta. And at last, I want to say one more thing, that is delta. This can be given in the numerical problem, the value of delta, or by using the property of the material, given material of the spring. Okay, if material of the spring is known, then delta can be calculated. We know that Young's modulus E. For example, yes, this is also visible. We know that Young's modulus E, that is equal to stress by strain. Am I right? Stress by strain. Okay. And stress is what? That is equal to force per unit area, W by A. W by A, that is the force per unit area, and strain is equal to delta by length of the spring. Okay. So by using this is Young's modulus, this is the property of the material, okay, by which the spring is made. So this is Young's modulus, and this is a property of the material, so this is known in literature. This can be obtained from the literature, and this is weight, this is the cross-sectional area of the spring, delta is the deflection, L is the original length. Original length means this length, okay, when there is no weight attached at the end of the spring, that length is called the original length. So by using this expression for Young's modulus, we can calculate delta by, for given weight and given length and given cross-sectional area, we can calculate delta. So that delta can be used here to get all the values. Okay. Anyway, this is the end of this lecture. Thank you for watching this video, and if you like my video, then please subscribe my channel. Okay, and of course press the bell icon. So if you press the bell icon, then what will happen if you press bell icon? In that case, as soon as I upload a new video, you will get immediately the notification of the same. Okay. Okay. Anyway, I hope everything is easily understood by all the students who are watching my video. Anyway, one more thing I want to add at the end of this lecture, that you will get in all my videos two names, Sangita Ghanti and Dipak Shah. Here I am Dipak Shah delivering this lecture. Okay, and Sangita Ghanti is behind the camera. Actually, behind the camera means what? Due to the presence of her, she is a lady, due to the presence of her, I have got inspired to make these videos for the students spread over the globe. Okay, anyway, already I have told so many things here, so I think I should finish here. Okay, otherwise you will get me bored. Anyway, thank you for watching this video.